Welcome to my third week of my video tutorial lecture series on 2D video game development, and specifically programming. I'm Tom Robertson, and we're actually going to get into an actual game this week. It's going to be very exciting. It's going to be full of really cool, interesting algorithms and concepts that are kind of central to video games. But it's still very much about code, and it's still very much about C# 2010 Express Edition from Microsoft, which is free on the web. And of course, we're also going to use the XNA 4.0 software tools so that we can quickly and easily make games. Just like previous weeks, we'll be creating a program and we'll be downloading files off the website that will give the program a certain amount of functionality that we'll explore together. So here I am on my desktop, and the first thing I want to do is create a new project. I'm going to go to C# 2010 Express Edition, and as usual I'll say new project. New project. Now this particular new project that I'm going to make is called Dungeon. That's cool. Everybody should make a video game called Dungeon. Right. And now, of course, as usual, the development environment, the IDE, builds a complete functional but empty program for us. And all I have to do is hit F5 or press this little green arrow on the toolbar, and I get my blue screen of happiness. A functional yet empty and does nothing computer program. So, again, as in previous assignments, I'm going to go to my website and download the content and program files that go with this particular assignment. So here I am on the Project Dungeon page of the website. I'm going to click on the code and data file. It's a zip file, and I open it up, and we see we have 2 program files and 4 art files. .png, which is a standard format for 2-dimensional image files. So I'm of course going to take these 2 .cs files. .cs means C#, and extract them. Dungeon is the particular folder that I want to place my .cs files in. Yes, I want to copy over the existing game1.cs. Now my 4 PNG files I'm going to copy, but I'm going to copy them into the slightly different directory of dungeon content. Great. I've copied all my files into their correct locations in the project directory structure. But of course, as we know, we don't just have to copy the files to the correct directories, we have to add them to the project using the Solution Explorer. So I'll right click on Dungeon Content, add existing item, take all these pictures. They're really tiny. There's not very many of them either. And then of course over here on Dungeon I'm going to right click and add existing item and add the helper121 code to the project. Now finally, of course, just in previous projects we're using helper121, which requires a font, so we'll make one. Go to Dungeon Content, right click, add new item, because we're making it sprite font, we don't have to change the name, and we hit add. Alright, so if I've added all my code and all my data and the sprite font to the project correctly, then it should run and have a functional game. Let's find out. Yeah, there we go. This is Dungeon. You can see you have a little knight, and you can move right, left, up, and down with the arrow keys. And when you move, the wizards also move. The only other really interesting and critical thing about this is that when I try to move right, I am unable to. Can't move right because there's a wall there. So I'm in a very small dungeon with 3 scary looking wizards. I guess I'm the knight. So, wow, that's cool. How does it work? Well, let's get into it. Let's get into the code and find out what's going on here. And as we get into the code, I'll also talk about some of the theory behind a cell-based game, which this is, and a turn-based game, which this also is. So if we get out of the program, I'm going to go ahead and look at game1.cs. If we look at the top of the game1.cs file, we've seen this stuff before. We've seen how it creates a game1 class in the namespace of our project, and it creates things like the graphics manager and helper121. This is interesting. We've got data for our map. This has a couple of constants, map width and map height. Why do we use constants? Because they look just like normal variables. Well, it's the const keyword that makes them constants. And there's only one real difference in terms of code functionality between a constant variable and a normal variable, and that is that once you set a constant to a certain number or value, you can never set it again. Now, who cares? Because you could set a variable and then just decide never to set it again, so who cares? Well, you care a little bit because the program understands that it's a constant value and does certain things in the compiler that make the whole game run a little bit faster because it understands that the variable is never going to change. That allows the compiler to do some fancy tricks that speed up your code. So that's worth doing. But another reason is that when you get into more complex programming and you work with other programmers, then you quickly find that all of your assumptions about what you should do and what you could do and what you won't do kind of go out the window. And that's where the structures of your programming language that keep you from making simple mistakes, like using consts so that you don't overwrite a value accidentally, become much more important in a multi-programmer environment. In fact, the more you work with other programmers and the more you work with lots of other programmers at the same time on the same piece of code, the more regimented your coding structure usually is in the everyday world of collecting a paycheck. But for this instance, in my mind, consts are simply something that I normally use when I want to replace a number in a code that I use over and over again with a word or variable name that's much more descriptive than the number. In my code I could have lots and lots of 1s and 10s and 15s and 2033s. But the truth is that if I come back to my code 6 months later when I've forgotten everything, or maybe if somebody else looks at my code, they'll say, 233? What is that even? I don't even know what that is. But if you replaced the number 233 with a constant variable name that said fuel left in lunar lander, or lunar lander fuel, all one word, of course, because a variable name can't have a space, then everyone else and yourself, you look at that and go, oh, lunar lander fuel. I know what that is. I know, 233. That's a pretty good value for how much fuel I have in my lunar lander. You see, that's mostly what const variables are for. Const values replace numbers that we sprinkle through our code that lead to confusion with actual names that mean something and are much more understandable to us. So in this case, we've got two consts, map width and map height. And oh look, we use them almost immediately right next to them in the code for defining how high and wide this two-dimensional integer array is. So this is C#. This is the way you make arrays in C#. You don't have to initialize them initially, but in this case we did because it's awesome to make a little map right here in the code. You see we initially defined it as an array of integers. It's got 2 dimensions because it's got a comma in there. Here's the actual name of the array. It's called map array. And after we're done with that, here we are instantiating the array. In other words, we didn't have to, but again, we're going to in this case. We made a variable, and now we immediately fill that variable with an actual two-dimensional array. And at this point, we have to say how big it is, how high it is, how tall it is, and how wide it is. We could have written 10 comma 10 here, but that would be less expressive. That would be more confusing, which is a really good reason to use constant variables. So now that we've actually defined it, we not only define it, we fill in the blanks. We actually initialize our brand new two-dimensional array with actual values. And if you see, it's real simple. It's 1 if it's a wall, or 0 if it's not. And that actually really works for this in this case. It's a very elegant and standard way of making cell-based grid world spaces for our objects to do things in our video game. And this is very common in video games. I can't tell you the number of times that you, as a video game developer, are going to be making a two-dimensional array of 1s and 0s or whatever so that you can build levels for your game. It's just how things get done, especially, you know, at the beginning. So now that we've made our map, and it looks kind of cool, then down here we have a bunch of variables. Notice that we have a bunch of const variables, which again, they're just numbers, but they're not supposed to change. And if they do change, if we do actually try to assign them some other number deep in the code, the program will crash and say, no, you can't do that, which is a good thing in this case because we don't want these values to change. We want them to stay the same, and we want them to be descriptive so that we can look at them in the code and figure out what's going on. In this case, the important thing is total objects. We've got 4 things in this world, and having played the game already, we know what those 4 things are. We've got a knight and we've got 3 wizards, right? That's 4 things. So we've got a couple of arrays, and these arrays basically are just the X and Y positions of the wizards and the knight. The X and Y positions of all of the objects in the game. It's easy to believe that the only variables that define the wizard and the knights right now is their position on the map. And guess what? That's exactly right. There's really one other thing that defines them, and that's their position within the array, which we're using as the placeholders of whether it's a knight or a wizard. But other than that, right now the only thing that makes a knight different from a wizard is its place in the array, and the only thing that makes them the same is their position. We literally currently are holding no more data. There's no hit points, there's no whose sword are you carrying, there's no armor points, there's no speed, nothing like that is currently in the game. Obviously, that's something we could change in the future, but you know, you look at this code, that's all we got for now. And you can see that this code is X and Y, and so you can see that the player starts at 7, 7. Now if we look here on the map and assume that this is 0, 0, then we can count 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's good. It looks to me like we're going to start off on a space that is empty and not a wall, which would be nice if we start where there's not a wall. Similarly, we start the 3 wizards mostly in the upper left corner. That's how we define the wizards and the players. So let's look down at this code. We've got a few more things going on here. There's a turn timer, and I'll get into why that's important, and an object turn counter. That's, as this comment suggests, and comments are good, that this object turn counter keeps track of whose turn it is. And it's very simple. We'll just go up the list, 0, 1, 2, and 3, and then back to 0 again. Everybody gets a turn. And by the way, we want some random numbers just so that the wizards can move around in random numbers or random directions. That's why we created this random object, which is built into X and A. So here's our constructor, here's our initializer, here's our load content, where all we basically do is set up a sprite batch and a helper. Unload content, now we've got into update. Update fits on the screen very nicely. What's going on in here? Well, I just said that we pay attention to turn timer, and that's true. Every time we're going through turn timer, we will subtract from it. And when it gets to 0, something happens. That's how our code is set up. First off, we test. if turn timer is greater than 0, then our next lines here says subtract it. Now, what is this subtracting? This seems awfully big, but what's really going on here? Well, here is game time dot elapsed game time dot milliseconds. Where did the game time variable come from? It was passed in, and it's always passed in when you're doing this XNA C# business. You see here in the update function, you always get a variable called game time passed in as an argument, and you can look inside that variable. Inside it, there's very useful stuff, including an elapsed game time variable, which contains a milliseconds variable. What does this really mean? Well, I've never really gone into great detail about this so far in our tutorial series, but there's no doubt that the update function and the draw function in your game1.cs are not called once. They're not executed once. In fact, they're executed over and over and over again until the end of the program, and they're executed very quickly. I wouldn't be surprised if both of them were executed 100 times a second. How fast? That's entirely up to the computer you're using. It's up to how complicated your program is and how much time it takes the computer to run it. It's about how fast the video card is, what other things are going on in the computer. With a modern Windows PC, it's very hard to get what is called an accurate frame rate, or how many times per second the screen updates. So most of what we do as programmers is tolerate this assumed variable frame rate. If the computer's going a little slow, we make our application run a little bit faster to compensate. If we're on a screaming fast computer, we might try to make the screen a little prettier, but we also might slow down our simulation of the game physics so that the game doesn't go so fast that it's unplayable. And there are different techniques that we'll explore in this tutorial series for doing that. But for right now, the important technique is to find out how much time passed since the last time the update function was called. And guess what? That's exactly what this code does. Game time, elapsed time, milliseconds tells us how many thousandths of a second have happened since the last time we were here in this code. Assuming, of course, that we understand that this update function just keeps going over and over and over 100 times a second or more. So why do we use this value? Well, it's milliseconds of elapsed time. If it goes 100 frames per second, which is to say the update function that we're writing here now is called or executed 100 times every single second, then that means that since a millisecond is a thousandth of a second, then 10 milliseconds have passed since the last frame. So, and if 10 milliseconds have passed since the next frame, then what does this mean? This means that we've got 10 divided by 1,000 times 3. So what's going on? That's actually a very small amount of time. 10 divided by 1,000, that's like 1/100th times 3. So 1/300th is the value that we're subtracting from turn timer. But that's okay, because if you look at it, when we actually move and do something, and we start a turn timer again, we set turn timer equal to 1. So we're counting down from 1 to 0, which means that each individual countdown probably doesn't have to be very big. It can be a fraction of 1. And in fact, that's exactly what we got here. Assuming a 100 frames per second frame rate, this math right here suggests that we will be subtracting 1/300th from this turn timer. So we could obviously tune this if we wanted the moves to go faster, but this here tells us how fast each frame is being run by the computer. This here is a countdown timer that we've used to separate when each unit moves in our game. So for now, let me actually fire the game back up And I'm going to move my knight around, and you can see that there's a delay between me and each of the wizards taking their turns and moving. And that's exactly the delay that this turn timer is setting up for us. So here's turn timer. When it gets to 0, the delay is done. Well, actually, it's not 0 yet. And then we subtract a number. And now, did it get to 0? Yes. So now we get to do this code. What do? Okay, we move to the next object. We move to the next wizard or player in the list. It's their turn now. And of course, if this value, this object turn counter, gets too big, then we'll wrap it around to 0 again. In this particular case, this piece of code then says if it's a wizard whose turn it is. If the wizard has a turn, if any of the 3 wizards have a turn, then what do? We move the wizard randomly, and this argument is which wizard, and we reset the turn timer to 1, ensuring another small delay before the next wizard or player gets their turn. So the actual wizard's whole turn is taking place in this function called move wizard randomly. It's really taking place in here because the wizard theoretically could do other things besides move randomly, in which case we might not want to put that code inside the move wizard randomly function. But we could make another function called wizard does something, and then inside that we could maybe put the function move wizard randomly. So here we are. This basically lets all the wizards take their turn. But if we see here, and this is separate from the whole turn counter kind of business, here's where our player is going to take their turn. What we're going to say is if the object turn counter is about a player and turn timer is 0 or less, then it's time for the player to do something. Specifically, our player reads the 4 keyboard inputs and moves the knight around, right? So there you go. That's what check it player input is for. And then we're done with this function. Now, move wizard randomly and check player input are both functions that we have in this code. They're functions we haven't looked at yet, but if we scroll down a bit, we'll find them. So here's my draw function. And it's actually fairly straightforward, but we really haven't done a lot of logic inside our draw function. We will, and there's no reason really not to do complex thinking inside our draw function, other than the draw function is really about drawing and not necessarily about game logic. But in this case, you'll see that we use for loops, no problem, because there are things that for loops are really good for in drawing.